Okay, now the one thing I did not put with the packet, I don't think I did. Yes, I did. I put some polar graph paper in there for you. You'll have the polar graph paper to do your homework for today. The very last topic that we will cover in Trig class is what is called polar coordinates. Every day that you came into this classroom, you walked by a chalkboard, you had a pencil sharpener there, and the chalkboard, you had basically Spidey's web there. You had a spider web graph on the back chalkboard. That is what we call polar coordinates. The idea of polar coordinates. When dealing with polar coordinates, it's sometimes easier to deal with polar coordinates when dealing with graphs. A lot of curves that go into graphs, are a lot easier to deal with in polar coordinates. A lot of the old style computer graphics that were on computer games were done in polar coordinates, because once again, it was a lot easier to deal with things in polar coordinates than it was in the XY coordinate, which is called the Cartesian coordinates. That's the XY that we typically deal with and work with. And the polar coordinates are a little bit different. And we'll look at, first off, graphing with polar coordinates, and then we'll look at converting between polar and Cartesian coordinates as the class finishes up today. So what we have here, once again, hopefully you got your notes out. And if you did not, I posted them so you can print them out. The first sheet that you have is you have Spidey's web here on the paper. We need to be able to put our coordinates in here that we will be dealing with. Where if we had the XY coordinate system, we would make little hashes and go out 1, 2, 3, 4. Or if we have theta and y-axis, we have on the theta axis we had 0, 90, 180, 270 when we're dealing with graphs. Well, when we're talking about a polar graph, we need to be able to get coordinates down also. Now, the nice thing about the polar graph is it is an east reference. So our degree measure on the line that goes to the right is going to be 0 degrees. That will be 0 degrees. Now, in polar coordinate graph paper, there's a lot of different polar coordinate graph paper that you have. This one will count out by 15 degrees. So this would be 15 degrees. This would be 30 degrees. This would be 45 degrees. This would be 60 degrees, 75. This would be 90 degrees. We'll just count out by 30s now. 120, 150, and 180 degrees. And this is just very similar to our east reference rotation, what we've dealt with throughout. Then we have 210 degrees, 240 degrees, 270 degrees, 300, and then 330 degrees, and then we move back to 360 degrees here. This is the amount of rotation that we are going about our center point. Now the center point is called the pole. You can think of this like if you would take a globe. If you would take a globe and cut it at the equator and then flatten out the northern hemisphere. Or if you're looking straight down and on top of the globe, what you would have is you would have the North Pole. And that's what this point is here, is the North Pole. It is what we are rotating about. We have our degree measures about this pole: 0, 30, 60, 90, 120, 150, 180. We rotate about the pole. So if we take a look, we have two values that we have to deal with. We have a value of theta, which is an angle of rotation. What is our angle of rotation about the pole? And then we have this R value. This R value is your distance from the pole. How far are you away from the pole? So we have two values here. We have an angle of rotation, and then we have a distance from the pole, which would create an ordered pair. And this ordered pair is going to be r theta. This will be r theta. Now this distance from the pole, what do we do with this distance to the pole? Well, that's what these circles are for. These circles are to count out your distance from the pole. And you can label these circles any units you want. You can just increment it out. I'm going to use every circle as a half unit. So this would be unit 1 unit away from the pole. This would be 1.5. This would be 2 units away from the pole. This would be 2.5 units, and this would be 3 units away from the pole. And if I take a look at this circle here, this circle is all 2 units away from the pole. Because our definition of circle is a set of points that are equal distance from a given point. Well, the given point's going to be the pole. And this circle is a set of points that are 2 units away from the pole, or 1 unit away from the pole. Now, if I wanted to, I could have started with this circle and said this is unit 1, unit 2, 3, 4, 5, 6. I could have labeled them that way. Now, how do we plot points on the pole, on the polar coordinate system? Well, if I have the ordered pair 230, okay, this means my theta value is 30 degrees, my radius is 2. So if I would go to my 30 degrees, which is up to here, this would be the line I'm looking at. I'm going to count out 1, 2 units from the pole. So this would be the ordered pair 2 and 30. Now, if you wanted to count out 2 units first and go to the 2 units or unit of 2 circle, and then go up to 30 degrees, that is fine. Or if you want to go to the 30 degree line first and count out 2 units, that is fine. You could do it either way. It's just like plotting XY coordinate systems. You could go out X and then up Y, or you can go up Y first and then out X. It does not matter. There's always more than one way, once again, to skin the proverbial cat. So if we look at the ordered pair 3 and 120, we're going to go over to the 120 line, and then we're going to count out 3 units. Or if I want to count out 3 units here, and then rotate all the way to the 120 line, this would be the ordered pair 3 and 120. Now what I want you to do is plot the ordered pair 1 and 210. Go to the 210 line and go out 1 unit on the 210 line. Here's my 210 line here. I'm going to count out 1 unit. So hopefully you place it at this point there. Now the question is, what do we do with the last ordered pair? We have -3 and 300. Well, if I take a look, I go to my 300 line, I go out 3 units. That would put me there. I go to my 300 line and I go out 3 units. So here's 1 unit, here's 2 units. This would be my 3rd unit right here. Well, that's +3 and 300. The question is, what do you think we should do if I had a -3 there? What would we do when we have the -3? Well, when we talk about negatives, that negative sign, that also means the opposite. The opposite. I still want to go to the 300 line, but if I go out +3, I go down along the 300 line. If I go -3, where do you think we go from the pole? I'm at my pole, and I want to go +3 goes out, the +3 goes along this line. What would be if I go -3? Courtney, what do you think we would do if I would go -3? Rather than going out the line here, or out the line here with a +3, what do you think we should do?
Go the other way past the pole?
Yeah, go the other way. So we go up the other line. So you might want to put up a straight edge. Here's my 300. Rather than going out the 300 line, I'm going to go the opposite direction. So I'm going to go really out the 120 line. So I'm going to come out to this point right here, and this would be the ordered pair, -3 and 300. So what we have is we have a dual point there, a dual ordered pair for the exact same point. When you have the negative, it just tells us to go, it's SpongeBob opposite day. Okay, SpongeBob opposite day. We just do the opposite of going out +3. We go -3. Well, if I go -3, I'm going up the 120 line rather than down the 300 line. Let's take a look at doing some polar coordinates, doing a polar graph. Let's go to the back side of the notes. Let's label our numbers. We have 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, and 330. This would take me back to 360. I'm going to still label every other circle. So this would be 1 unit, this would be 2 units, and this would be 3 units. We want to graph the equation r equals 1 plus 2 cosine theta. Now, there's not going to be an easy way of doing this. I know when you have y equals 2x plus 3, yes, initially we got ordered pairs, and we plotted ordered pairs, but then we learned how to go slope and y-intercept. You found the slope and the y-intercept, you plotted the y-intercept, and then you went up your slope. Okay, so we found easier ways of doing things. Well, when we're talking about polar coordinates, there's really no easier way of doing it. So what you're going to need to utilize is your calculator here. I could not get my calculator to work here. Hopefully it'll work now. It's just not wanting to work for me today. So you're going to want to pull out your calculator. Make sure you're in a degree mode. And all we're going to do is we're going to plug in values of theta there. So in the first one, we have 1 plus 2 cosine of 0. So we have 1 plus 2 cosine of 0 degrees. So you want to clickety-clack that through the calculator. 1 plus 2 cosine of 0 degrees. And you should come down to a value of 3. What I want you to do is do the rest of your theta values. And once again, what this will create is this will create an ordered pair. This ordered pair will be r is 3, theta is 0. If we put in 30 degrees, 1 plus 2 cosine 30. We get 2.7. So we have an ordered pair of 2.7 and 30. Okay, go ahead and fill out the rest of these ordered pairs, these R values. You get an ordered pair. Then what I want you to do is I want you to graph each one of these ordered pairs. So when I'm at 0 degrees, I'm at 3. When I'm at 30 degrees, I'm at 2.7. So this is 2.5 here. So at 30 degrees, I'm at 2.7. So what I want you to do is create the rest of your R values, plot the points, but do not connect them together yet. So go ahead, find your R values and plot the ordered pairs. Isaac Wangard, if I go down my list here, what would be my R value for 60 degrees? Just read down your values.
2, 1, 0, negative 0.73.
180.
Negative 1, negative 0.73. 0, 1, 2, 2.73, 3.
All right, so now we look at our graph. Okay, when I'm at 60 degrees, I have a value of 2. Then we have a value of 1 at 90 degrees. So at 90 degrees, I'm just going out 1 unit. 120, I'm at 0, so I'm at the pole. At 150, we got to go negative 0.73. So at 150, I got to go backwards my 0.73. At 180, positive 1 would take me to there. Negative 1, I have to go backwards. 210, I have once again negative 0.73. Then we're back at 0. At 270, we are at 1. At 300, we are at 2. At 330, we are at 2.73. And at 360, we're back at 0. I'm back at 3, my bad. So what we get is we get a bunch of points here. You get a bunch of points that we have. Now, how do we connect the dots, la, la, la? Well, once again, we're going to be dealing with some curvature here. When dealing with curvature, when you're dealing with the polar coordinates, how do we graph here is we start at our 0 and then go numerically around our polar graph paper. So we go 0, 30, 60, 90, 120. So we're going to start here at the 0. We're going to go up to 30, 60, 90, 120, right to 0. Then we go 150, so we're going to continue through, back to 0. Then continue for the rest of our graph. This here is called a limacon with a loop. Sort of like a lima bean, a limacon. And we have a loop here. So we have a limacon with a loop. We also have limacons without the loop. That's my Irish accent for the day. So we have limacons with and without loops. You'll get cardioids. Once again, it is going to be a curve. You'll get 3 and 4-leaved roses, which is once again curves. Now, if we take a look at this equation, r equals 1 plus cosine, or 2 cosine theta. It is not a very difficult equation to deal with. But if you were dealing with this in an XY coordinate system, and you wanted to get the exact same graph in an XY coordinate system, let's see here. Let me do a little manipulation. R equals 1 plus 2 x over r squared, x squared plus y squared is equal to square. So if I was looking at an equation in an XY coordinate system, the equation would be x squared plus y squared minus 2x is equal to the square root of x squared plus y squared. That would be your equation in an XY coordinate system. So you would have to substitute in a value of x and be able to solve for a value of y, or substitute y and solve for x, which is not a very easy task to do. Dealing with it in r equals 1 plus 2 cosine of theta, that's a little bit easier to work with, which is nice. That it, once the computer graphics that are done, that were done, the arcade computer graphics that were done, use all the polar coordinate systems to be able to graph circles, ellipses, anything with any type of curvature was done with a polar coordinate system. In your first part of your homework for today, you'll be using the polar graph paper that I gave you. You'll be plotting points initially, and then you'll be dealing with some graphs also. So what you want to be able to utilize is this idea of getting r's, or using these theta values, and then calculating your r values. Now, when you get to the 3-leaved and 4-leaved rows, what's going to happen is you will just start at 0, you come to here, you go to here, you go to here, go to here. It will start looking like an X. It will just keep on repeating itself just with an X. What you're going to want to do with that is do intermediate values. Do every 15. But then with only doing every other, or doing every 15, you will not have to go beyond 180 degrees. You won't have to do the second half over here, all these points. You'll just have to add in additional values over here. The 15, 45 go 0, 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165, and then 180. And that will get you your 3-leaved or your 4-leaved rows. That's the first part of your homework. And once again, you have the polar graph paper that is there that you can utilize. Now, the first problems 1 through 8, when you're doing problems 1 through 8 in the book, they're asking you to just plot the points. Just take one graph, one of the graphs, and just plot the point and do an ordered pair there. The second part is, once again, you're going to be dealing with these graphs. The second part of the assignment for today deals with how can we, I went through conversion of, I had an r theta equation, I put it into an xy equation. How do we go about doing that? And that's what you'll be asked to do in the second part here of your assignment. When you're dealing with x and y, this is called a Cartesian coordinates. And this should be your second set of notes that was in your packet. So when you're dealing with x and y, you're talking about Cartesian. When you're talking about r's and thetas, you're talking about polar coordinates. So you have r's and thetas, that's polar coordinates. You have x and y's, which is Cartesian. And typically what we deal with is we deal with x and y's. But once again, there are avenues, or there are arenas and areas where polar coordinates is a lot easier to work with. What we have here is we have our polar coordinate system, and then I put in an x and a y axis. So we have an x and a y axis, and we also have a polar coordinate system here too. if we would take any point, doesn't matter where I put the point, we can label this point going out x. I could go out x units, and then from that point, go up y units. So we can move out x and then vertical y, and label this ordered pair x and y. We can also label this point by saying I'm going to rotate r units. So I can rotate, theta units. I can rotate this theta units and go out r number of circles. So we can also label this point, I'm going to rotate theta and move out r. So we can also label this point r and theta. So this point in a Cartesian coordinate system can be labeled x and y. We moved out x units here and moved up y units here. Or in r theta, we rotated theta units here and we went out r units from the pole. So there's two ways of labeling this one point. Well, what we have just created with these two magical things is a right triangle. And if we have a right triangle, we have our good old buddy Pythagoras that still is with us. If we look at our right triangle and our good old buddy Pythagoras, we can get relationships that will connect the r and the theta with the x and the y. If we take a look at this triangle, the cosine of theta in this triangle. Bennett, did you ever make it in?
Yeah.
What is the cosine of theta in this triangle? I have x here, I have y there, I have r there, and I have theta there. What is the cosine of theta?
Is it y over r?
What's cosine defined to us as?
Adjacent over hypotenuse.
Adjacent over hypotenuse. What's adjacent theta? What's the hypotenuse?
X over r.
X over r. So the cosine of theta is equal to x over r. Multiplying both sides by r, we have x is equal to r times the cosine of theta. What this does is this gives us a relationship between our polar coordinate system, r and theta, and our Cartesian coordinate system, x and y. If we take a look at the sine of theta, Lexi, looking at our triangle, what is the sine of theta equal to in our triangle?
Y over R.
Y over r. So we have y over r. Once again, multiplying both sides by r, we have y is equal to r times the sine of theta. Once again, a relationship that allows us to take x's and y's and moves it into r's and thetas. If we look at the tangent of theta, Emma, what is the tangent of theta?
It would be y over x.
Y over x, that is correct. So these are relationships that, once again, take our polar coordinates to Cartesian or Cartesian to polar. And then we have our good old buddy Pythagoras. Our good old buddy Pythagoras. What would our good old buddy Pythagoras say about our triangle up here? Molly, what would our good old buddy Pythagoras say about our triangle?
I'm not sure.
What would be our Pythagorean theorem say about this triangle?
It would be x squared plus y squared equals r squared.
There you go. X squared plus y squared is equal to r squared. Our good old buddy Pythagoras continues to help us. And what we can do is we can transfer this also into taking the square root of both sides. R is equal to the square root of x squared plus y squared. What these are relationships that allow us to be able to go from Cartesian xy's into polar r's and thetas, or vice versa, r's and thetas back into x's and y's. So if we take a look, let's convert to a polar or Cartesian coordinate system. We have an equation r equals 6 sine of theta. That is polar coordinates. We want to change this into an xy coordinate system. Well, if we take a look, this here, r is equal to square root of x squared plus y squared. If I would substitute that in right away, that would get us really ugly, because I do not like dealing with radicals in my equations. So I save that for the very end. But if I take a look at my right-hand side here, I have sine of theta. So what we're left with here is r is equal to 6 times the sine of theta. And from up above, the sine of theta is equal to y over r. Now, if we would take both sides and multiply by r, just clearing our fractions out, we're left with r squared is equal to 6y. Now, the reason why I don't substitute in that radical to begin with, because you never know when you might turn into something a little bit easier to deal with. And the something easier to deal with is this r squared. R squared is equal to x squared plus y squared. So making a substitution, we have x squared plus y squared is equal to the 6y. Now, typically, a standard form to this is fine, but a standard form is you get all the variables on one side the equal sign and all the constants on the other. So we have x squared plus y squared minus 6y is equal to 0. But once again, if you had that down there, I would not count it wrong. Okay, now what I want you to do is follow these steps that we just did here. Follow these steps and do the exact same thing for r equals 4 cosine of theta. But now we're dealing with cosine. So first substitute in for your cosine of theta. From up above, what is cosine of theta equal to? You'll be able to multiply both sides by r. And then substitute in for the, should get an r squared there, substitute in for it. Just follow the steps that we just did over here. Follow these steps for this problem. Cadence, you ever make it in? Andrew, you ever make it in?
Yep.
Andrew, what do you come up for a solution?
X squared plus y squared minus 4x equals 0.
That is correct. That is correct. Following the same method that we just did over here, you get the exact same, not same solution, but very similar solution. And once again, if you had x squared plus y squared is equal to 4x, I would accept that too. Okay, let's go to the bottom. Now, if we take a look, we have a fraction here. Once again, when we have fractions, they get a little ugly. So let's use our properties of equations and let's clear the fraction out. Let's multiply both sides by our denominator. So we have 3 minus cosine of theta that we're multiplying to both sides. So we're left with r times 3 minus cosine of theta is equal to the value of 5. Now let's do the exact same substitution. Let's get rid of the cosine. Okay, cosine from what we did up above is equal to, the cosine is equal to x over r. Same type of substitution. Now let's use our distributive property. Let's distribute our r to both these terms. So we're left with 3r minus, well, if I multiply x over r times r, these r's will cancel out. So we're just left with 3r minus x is equal to the value of 5. The problem we run into is we still have an r in there. We still have an r. Well, when we did the first ones up here, we had an r squared here, which was an easy substitution, x squared plus y squared. We don't have that anymore. We just have an r. So the only substitution that we can put in for that is the square root of x squared plus y squared. Now what I'm also going to do is I'm going to take the x to the other side. So we're left with x squared, or x plus 5. Once again, this gets a little bit messy to deal with. We can just leave it in this form with the radical there, but typically that's not acceptable. So we can multiply, or we can square both sides. Square both sides. We have multiplication here, we have addition over here. When I have multiplication, we distribute over the multiplication. So we have 9 times x squared plus y squared. Over on the right-hand side, we have to take x plus 5 and multiply it by x plus 5. Okay, once again, this is just algebraic skills that that you worked with in back with Mr. Reed, Dr. Reed, and also with Dr. Clark. So if I FOIL this out, we're left with x squared plus 10x plus 25. Once again, you want to collect all the variables on one side and the numbers on the other. Our next step would be to distribute. So we have 9x squared plus 9y squared is equal to x squared plus 10x plus 25. Taking your x squared over, we could subtract x squared and subtract 10x. So we're left with 8x squared plus 9y squared minus 10x is equal to 25. Once again, when we throw this, when we don't have an r squared in there, the problem just becomes a little bit more lengthy, and you have to have patience to go through the problem. If we go to the back, I'm not going to worry about this right here. If we were in class, actually in school, I would worry about that. But don't worry about the type of conic sections that we have. What I'd like to do is go down to my last problem here, where we are putting the process in reverse. We have Cartesian, and we want to put it back into polar coordinates. From the front side, we have x is equal to r cosine of theta, and y is equal to r sine of theta. Well, what we're left with is an x squared plus y squared here. So if we make a substitution, we have r cosine of theta squared plus 8r sine of theta all squared is equal to 16. Once again, using our properties of algebra. This is multiplication. When we have multiplication, we can distribute exponents over both of the terms. So we're left with r squared times the cosine squared of theta plus 8r squared times the sine squared of theta is equal to 16. when you're solving for polar coordinate equations, typically they are in the form of r squared equal to or r is equal to. It does not matter. So to get in this form, we had a common factor of r squared in both of these terms here. We can factor out the greatest common factor. So we have r squared cosine squared of theta plus 8 sine squared of theta is equal to 16. Dividing both sides by cosine squared theta plus 8 sine squared of theta. What we are left with is r squared is equal to 16 over cosine squared theta plus 8 sine squared theta. Now you might sit there and say, well, that equation looks a lot more difficult than what we originally had. X squared plus y squared is equal to 16. And you know what? You're probably right. You're probably correct with that. But what we want to be able to do is we want to be able to create relationships that would work for both. Once again, this may be easier in a computer graphic system to be able to utilize a polar coordinate system rather than a Cartesian x and y. Your second part of your homework is on, I have it listed there. What you'll be doing is you'll be converting from polar to Cartesian and Cartesian back to polar. So that will be the second aspect of your homework. Okay, this is the last topic. This is the last lesson of Trig. Sort of makes me tear up a little bit, get a little misty-eyed. We've made it through the idea of the Trig class. We've made it through the Trig class here. Okay, if you need to grab a Kleenex and dab the tears from your eyes, that's fine. Go ahead. Or you can use your sleeve. This was the last topic, though. And once again, I gave 2 days of homework stuff for you to work on. On Thursday, we will have a review day. So our class will be very short on Thursday. I'll just have a review sheet for you. I'm pretty sure, I'm hoping. Yes, I provided the review sheet for you also. So in your packet, I will post it. I will post solutions to the review sheet also. And that will be it. Friday, we'll take the quiz at our normal time, and we'll just do our regular, I posted it there, our regular scheduled time at 12 o'clock or 10 o'clock on Friday. We will just do 10. It should only take you about a half hour to get through the quiz. If you've been working at this all, if you've prepared yourself at all, should take you about a half hour to get through the quiz. And that will be on Friday. And that will be the last evaluation that we do in the class. Questions? All right. I have nothing else for you for today. You should be working on your homework. Once again, Thursday will be a review day. Friday will be the quiz on this material. And QED, we'd be done. Yes. Yes. All right. There's no questions. If you want to stick around and ask me a question, that's fine. If not, you guys are dismissed. You're out for the day. Adios. Have a good day. Stay safe. Stay out of trouble.
Hey, thanks, Mr. Gregory.
Yep.
Yeah.
Yep. We'll see ya.
Thank you. Appreciate it.
Not a problem. It's been fun.
Yeah. Sorry, I was a little bit late, but I caught most of it.
That's
I'm
okay.
just late.
That's fine.
My fault.